The purpose of this lab is to use the data of the motion of a star to obtain the net force acting on the star by a black hole, to find the mass of the black hole based on Newton's universal law of gravitation. I will build a model to predict this net force acting on the star. Using Newton's second law, I did a Python model that uses a CSV file that contains the data of the motion of the star to compute the net force. In order for the model to compute the net force, it needs to determine the change in velocity, momentum, changing momentum, and changing momentum over changing time, which is equal to the net force based on Newton's second law. Everything else was obtained directly from the data. After determining all these important factors, the model also computes the dt parallel, which is equal to fnet parallel, and the dt perpendicular, which is equal to fnet perpendicular. In the end, I found that the model does a good job computing the net force and directly describes the system and its motion. By using Newton's second law, it describes the interactions of the surroundings by determining also the fnet parallel and fnet perpendicular. With this net force, I was able to determine the mass of the black hole by using the gravitational force formula and solving for m, and I got the result of 2.38 e to the 31 kilograms. Based on the fundamental principle of Newton's second law, net force is equal to the changing momentum over changing time. In order to find this net force, I needed the positions from the CSV file and divide them by delta t to predict the different velocities, which will give me change in velocity. With the change in velocity, I was able to calculate the momentum, changing momentum, and finally changing momentum over changing time, which is equal to the net force based on Newton's second law. All gravitational forces can be resolved in two components. Thus, the net force can also be resolved into two components. The fnet parallel component moves parallel to the direction of the motion and shows that the object is slowing down or speeding up. The net force is perpendicular component points in the direction of the center of the Kisin circle, that at the same time fits the motion, and it shows curviness in the object's motion. Newton's second law states that the net force on an object is equal to the rate of change of its momentum. Although they are equal to each other, net force deals with acceleration and it depends on a specific point and instant in time. On the other hand, changing momentum is an average of change between two instances and points in time, because you need an initial and a final value of velocity to determine this. This is the difference between these two values. This code follows exactly the same process based on Newton's second law, and using a given mass of 1.98 e30 kilograms and a delta t of 86,400 seconds. First, by using the velocity formula, it computes x and y, components of the velocity, by using the different x and y values of position of the CSV file and dividing them by the changing time. The c component of the velocity is equal to 0. With the velocity components obtained in the previous step, this model computes the initial and final velocity, and with it calculates initial and final momentum using the momentum formula. Then, it calculates the change in velocity and change in momentum. After determining the change in momentum, we can say that it is equal to the net force by using Newton's second law. At the end, the code prints the value of the magnitude of the net force. With this value, and using Newton's universal law of gravitation, I was able to find the mass of the black hole. Here's the value that the code runs and determines. The mass of the black hole is equal to 2.38 e to the 31 kilograms. The results I got show that the model does a good job. Fnet, which is the yellow arrow that we got here, points downwards through the motion. Fnet parallel, which is the black arrow, at first points opposite to the direction of the motion, but later it points in the same direction as the motion. Fnet perpendicular, which is the blue arrow, shows that the curviness of the motion and points to the center of the Kisin circle that fits the motion at that time. Based on Newton's universal law of gravitation, only when the mass of the black hole changes, the star motion will change. Since in this case the black hole is placed in the same location as the previous black hole, and we are assuming that the motion remains unchanged, the mass of the new black hole cannot be different from the mass of the previous black hole. Thank you.